Hello, this lecture is called Coordinatization Principle. And we're now going to discuss something that is directly related to what we were doing before in relation to this operator we call we call this is the Greek letter rho, and this operator is used to denote the vector representation. Okay, this is the representation, the vector representation, and whenever we usually refer to this has a thingy here that specifying a set that is linearly independent and spanning, and then this is reference or evaluated a specific member of a vector space. Well, this whole thing is assumed to be a vector of Cn, for example. Okay, so let's check what we have here. Suppose we have a vector space U, and that vector space has a basis B of size n. So this portion of the premise of this theorem is telling us that the dimension of the vector space U is n. Okay, so U is of dimension n, and that is going to be something that we're going to keep in mind, because this dimension is going to be directly related with the vector space Cn by means of these vector representations. These are vector representations on every member of this subset of U. So here S is assumed to be a subset of the vector space U, and this subset has members that are labeled or numbered from 1 through k. So S has k members. We don't know what those members are because we're assuming that this is a general vector space U. However, we are going to refer to the vector representation, okay, the rho sub b at u1, u2, u3, all the way through uk. We're going to refer to that vector representation. Each of those representations will be a vector in Cn with values. Each of those values assume here to be a complex number. That we understand quite well. And so what we want to establish here is whether or not this vector, whether or not this set of members of U, which each of these members U sub j is called a vector in the general sense of being a member of vector space U. So even though we don't know explicitly where these U's are, this vector space U could be a space of polynomials of degree n, or it could be a space of matrices, or it could be a space of functions. We don't know. It doesn't matter. This theorem here gives us a way of establishing linear independence of that subset S by means of establishing linear independence on this subset of Cn. And so that we know quite well. If we have a subset of Cn, these are supposed to be vectors of all equal length, and we want to know whether or not they are linearly independent. We stack those vectors as columns of a matrix, and then we compute the reduced row echelon form, and the reduced row echelon form would provide us with information as to whether or not those column vectors in Cn are linearly independent or not, right? And that's precisely what we would use here to then go back and establish that this set S is linearly dependent or linearly independent. So let's now consider the vector space P sub 2 polynomials of degree 2, and this set here D, which contains two polynomials of degree 2, is both linearly independent and spanning. In other words, the span, we can say that the span of D is exactly equal to P sub 2. So this set D is a basis for P sub 2, but we're going to first choose what is called, or could be referred to as the standard basis, another set that's also linearly independent and spanning, which spans P sub 2. And that set is what we're going to call here B. Okay, so these are the powers. So this is basically, not basically, this is x0, and here we have x1, and then we have x2. And so what will come next is to consider each member of this set as a linear combination of the basis elements of this basis B. Okay, so um, this is not difficult to do. So let's take a look here at the first polynomial, right? The first polynomial relative to this basis. This first polynomial is written as -2 times x to the 0 plus -1 times x to the 1 plus 3 times x squared. So making use of each member of the set B, we now are using coefficients -2, -1, and 3. And that's precisely what we want to do next. Think about those coefficients now being collected into a column. So -2, -1, and 3. Okay, that's precisely the first column we're going to write into this set. And so we are now going to consider a set that has rho sub b, the vector representation relative to this basis b of, remember what we mentioned before, relative vector representation relative to b, and then we refer to a point at which that representation we're evaluating that operator rho. So we're interested on the vector representation of this object relative to b, and that representation will be given by -2, -1, and 3. Okay, so that first vector representation contains numbers -2, -1, and 3 because those are precisely the coefficients needed to express this object as a linear combination of the basis elements of that set B. If we now consider the vector representation of this object here, we have to also take into account that this is 1 plus 0x minus 2x squared. Okay, so here we're going to have coefficients 1, 0, and -2, and those are precisely coefficients that we store on the second column. And then the next object here, 5 plus 4x plus x squared, is going to have a vector representation with numbers 5, 4, and 1. And so what comes next is precisely to take these three columns, okay, form a matrix, and find out whether or not these three columns are linearly independent. So it turns out that indeed, if we, and this is something that you should pause this video lecture right now, and you should pause it, you should form this augmented matrix, and you should compute the RREF, and you will find out that this matrix rho reduces to the identity matrix, implying, right? So implying that indeed this matrix is a matrix with columns that are linearly independent. So therefore, F is a linearly independent set. In fact, F is also a basis for C3. So these are the steps. Form a matrix we're going to call A, whose columns are the members of that set F, and you can verify that A rho reduces to the identity matrix with 3 rows and 3 columns, and sure enough, A is non-singular, and that implies that F as a set is a spanning set and also a linearly independent set that could be used as a basis for C3. And this is the contribution of the theorem that we're discussing, we're illustrating, that because F is a basis of C3, then D is also a basis for P sub 2. So we can see how F is completely, these are two different, these are vector spaces. C3 is a vector space. F is a basis for that vector space. D is a basis in a completely different vector space, which is a vector space of polynomials. Okay, so they're not two bases on the same space. However, the genius or the importance of this theorem is somehow a way of connecting them. There's some kind of mapping going on, and one provides information about the other one. Okay, so here is another example. Now let's consider a vector space of M sub 32 or M32. This is a standard basis for this vector space. These are matrices with 3 rows and 3 columns. Each matrix has a lot of zeros, and only one of its entries is equal to 1. So what we want to address here is this set S, S being equal to these two matrices, a linearly independent set in M sub 3, 2. And so let's now express one of the members of that set, okay, this matrix, as a linear combination, okay, it's a linear combination of the, well, you can see it's a linear combination of some other elements of that other set. And so you can see the what's going on here. It's well, finding out what is the linear combination is not that difficult. You can do that almost by inspection, because of the structure of each of those matrices having a lot of zeros and only one entry that is equal to 1. Okay, and so we can then use those coefficients, 3, minus 2, 0, 7, 4, and minus 3. We can store those coefficients into a vector. That's precisely what we have here. We can store those coefficients into this column vector, and that is the vector representation relative to B of that matrix. Okay. Similarly, for the matrix that has first column minus 1, 4, and minus 2, second column 3, 8, and 5, we can do a very similar thing of expressing that matrix as a linear combination of these matrices with a lot of zeros and 1, and then we'll find that the vector representation of this matrix is equal to this column vector. And so our best friend in the world, RREF, reduced row echelon form, will rescue us, will rescue the day here. We form a matrix with these two columns, each of them being the vector representation relative to a basis, and then we row reduce and find out that this is the RREF of this matrix with two columns, which implies that the set composed or made of the vector representations is a linearly independent set. And so the theorem that we're discussing in this lecture is establishing that the set S is therefore linearly independent.